Okay, great. So at this point, we are all sufficiently confused and have no idea what is going on. Okay, hopefully you have a little bit of an idea what's going on. My example here, just taking a look at the way that the computation goes. This computation is pretty straightforward, but why are we doing this computation? Let's see if we can get at that. Let me go back up to the previous example. And so we were looking at the limit as x approaches 1 of 2x plus 3 was equal to 5. And again, you gave me a tolerance of 0.01, and then I gave you a tolerance of 0.005. So to help us try to understand this, I brought with me my calculator, and let me show you how I set this up. In my first function, I have 2x plus 3, which is the function that we are taking the limit of. And then in the second, I have the absolute value of the function minus 5, right? So the function minus the limit. And what I'm doing is setting it up so that I can use this table. And what we'll see is that if I put in an x value, then I'm going to, in this column, I'm going to evaluate the function at that value. And then in the second column, I'm going to evaluate how far away that function is from 5. So, for example, I'm going to look at 1.001. Now, my point here is that this 1.001 is closer to 1 than my tolerance of 0.005. I gave a tolerance of 0.005. This is only 0.001. It's within that tolerance. When I select this, I get that the y value is going to be 5.002, and this error is 0.002. So for these values that I'm plugging in, what I'm going to say is that if my x value is within this distance, 0.005, then the y value, or this absolute value in the difference, will be smaller than that tolerance that you gave me. So if I did 1.003, that's within the tolerance. I get an error that tolerance of 0.006. That is smaller than the 0.01 or 0.01. If I go on the other side and do 0.998, that's close enough. That's less than 0.005 away from 1. Then I'm going to get 0.004, which is smaller than the 0.01. Also notice that if I plugged in exactly 1.005, that's as far away from 1 as I'm allowed to be, then I get exactly the tolerance that you gave me, 0.01. If I go on the other side, 0.995, I should see the exact same thing, and I do, right? It's on either side of the value of 5, but I get exactly that tolerance. So again, I go back to the beginning idea. What am I doing? I want to show you that we get really close to 5. So you tell me how close you want us to get. And in all of my examples, you've told me that you wanted to get 0.01 within the value of the limit. And then I tell you how close the x values have to be in order to get the y values to be within that distance. Okay, let's take a look at the graph and see if we can get a better idea about what it is that we are talking about here. So in the graph, right, so this is the graph. You'll see I've done this in Mathematica. I plotted 2x plus 3. Again, we're going back to that original example. I plotted it over the domain from 0 to 2, and I made sure that the origin was at the origin. And we were looking for the limit as x approaches 1 of f of x. So we're looking as the limit approaches 1. And it looks to me like, you know, that value of 5 ends up being right there. When you gave me that tolerance of 0.01, you were giving me a tolerance on the y-axis. How close do I have to be within 5? And then what I was giving you was a tolerance on the x-axis. How close do my x values have to be? So I've created the exact same graph, and just to point out here, I'm looking at this graph over the interval from 0 to 2. I've created the exact same graph. So in this graph, I really zoomed in. I'm only looking at values from x going from 0.95 up to 1.05. So this is really zoomed in on the graph. Don't think that that is the origin, because it isn't. You can see that, this is 0.96, this is 4.95. Mathematica always puts an axis into the graph by default, and it makes it so that if the axis doesn't intersect at 0, then it's pretty clear that it doesn't intersect at 0. So this is really, really zoomed in from the previous graph. You gave me a tolerance of 0.01, and you can see on my graph that above that 5.01 is right here, and 5 minus 0.01 is right here. And so you wanted me to be within 0.01 of that 0.5. All right, well, I am going to draw a couple of straight lines, and just because it's making me giggle, I'm holding a ruler on my computer so that I can draw a straight line. I'm going to draw that straight line there, and then another line right here. That is the interval that you gave me, right? You gave me 0.01 on the y-axis. And then in the x direction, I am getting these lines right here. This one and this one. And what is, I guess, pretty clear if you look at it, this point right here is going to be 0.995. So if this is 0.98 and this is 1, then there's 3 tick marks in the middle. Then this is going to be 0.995. And similarly, this point here is going to be 1.005, which were the values that we got when we were doing the math. Okay, this brings us to what is called the formal definition of a limit. Now, there's a whole lot of words and symbols here, and so you may want to just kind of pause and get all this written down, and then I'm going to talk through it, and hopefully we can see that everything that's written here is actually stuff that we have been talking about over the last several minutes. So here's the formal definition. Let f of x be a function that is defined on some open interval containing the point c, and we say except possibly at c, the function doesn't have to exist at the point that we're letting x approach. And let L be a real number. The statement that the limit as x approaches c of f of x is equal to L means that for each epsilon bigger than 0, there exists a delta bigger than 0, such that this statement down here is true. So before we get to that statement, let's just make a couple of points here. This is the Greek letter epsilon. And epsilon is always representing a small number. In fact, in the example that we have been looking at, I kept saying that you give me a tolerance, and we were using the number 0.01 as that tolerance. In our examples, that was the value of epsilon. And then this is the Greek letter delta. And delta was the value that I was giving you back. So you gave me a tolerance that was on the y-axis, and I gave you back a tolerance that was on the x-axis. So it means that for each epsilon bigger than 0, there exists a delta such that if the distance between x and c is less than delta, then the distance between the function and the limit has to be less than epsilon. All right, we're going to come back to that, and this is really confusing at this point. So if you're confused, then you're in exactly the right place.